Hello everyone, welcome to Infotainment Lounge. Today's video is for AS level students, chemistry students, and it is about the ionization energy and the factors affecting ionization energy. In fact, I would discuss the trends of ionization energies in the periodic table too. So stay tuned. Now, ionization energy has the basic definition of ionization energy is that it is the amount of energy required to remove an electron from the outermost shell of an atom. For example, suppose we have an atom. This is the nucleus of the atom. This is the first shell, then the second shell. Suppose we have 2 electrons in the first shell and 3 electrons in the second shell. Now, if considering this particular example in mind, this is the example of boron. Now, this electron, if we want to remove this electron from the outermost shell of an atom, of this atom, obviously it requires some energy. As we all know that it is moving around the nucleus, it is revolving around the nucleus with a particular speed, and when it has a particular speed, that means it has a particular kinetic energy, which actually balances out the nuclear attraction. That is why electrons do not fall into the nucleus. So if we want to remove this electron, if we want to take this electron further away from the nucleus, that means we will have to give it some energy. It will gain more and more kinetic energy, and it will get out of its orbit and stay away from the nucleus or the atom instead. Now, this energy that is required to remove this electron out of this shell is called the ionization energy, or simply the first ionization energy. Okay, now that was just the basic definition of ionization energy. Let us look at this, what is happening here. There was a boron atom which was neutral. Number of protons and number of electrons were equal in this atom. If we are considering that there are no other forces acting upon it except the nuclear attraction, that means this atom is an isolated atom, and the state with isolated atom is always gas. This means a gaseous boron atom was here and it lost one of its electrons, and when any atom loses an electron, it becomes a positive ion. So it lost one electron, so it gained a charge of +1, and again this positive ion is formed from an isolated atom. That means it is an isolated ion, so the state with this would also be gas. Okay, now from the basic molar concept, we know that whenever we are talking about balanced equations, we do not talk about atoms or molecules directly. These are molar ratios. See, this means 1 mole of boron's gaseous atoms lost 1 mole of electrons, and they became 1 mole of unipositive gaseous ions. So this takes us to the extended definition of ionization energy, which states that it is the enthalpy change when 1 mole of gaseous atoms lose 1 mole of electrons to form 1 mole of unipositive gaseous ions under standard conditions. Now, enthalpy change, as we all know, it is the net gain or loss of energy during a reaction. And why standard conditions? Because if we change the conditions, like if you are carrying out the same experiment at a different temperature or a different pressure than mine, that means the amount of energy absorbed or released would be a little different from that of mine. So we have to take standard conditions. Standard condition means 25 degrees C temperature and 1 atm pressure. Okay, now the first electron has been removed and we have a gaseous ion. This equation represents the first ionization energy of boron, which can be represented as delta HIE, and there is a sign of naught on the top of delta H. This naught indicates standard conditions. Now this is the first ionization energy. Now what if this boron ion loses another electron? Now if another electron is lost from the outermost shell, then the energy required for that electron to be removed will be called the second ionization energy, and the equation in this case will be, it will start from unipositive ions, of course gaseous, because we do not want other forces to change the value of energy, and bipositive ions will be formed, again gaseous, and only 1 mole of electrons will be lost. So this is the second ionization energy of boron. This is the equation for the second ionization energy of boron. Similarly, if we are talking about the third ionization energy, we'll start from B2 plus gas and we'll end up with B3 plus gas, with a loss of 1 mole of electrons. Okay, now the factors affecting ionization energy. There are 6 factors in total that affect ionization energy. 3 of them are major factors, and the major factors are atomic radius, nuclear charge, and shielding effect. You need to learn these factors in the sequence that I am writing these factors in, because this is according to the strongest factor first and the weakest factor at the end. So atomic radius is the strongest factor, then comes nuclear charge, then comes shielding effect. Now there are 3 minor factors which also affect the amount of ionization energy. First one is repulsion due to the electron pairs in the valence shell, then stability of a subshell, and the last one paired or unpaired electrons. I will try to explain all of these. First, let us look at the atomic radius. See, ionization energy is inversely proportional to atomic radius. Now why is that? Let us try to understand that. See, if there are 2 atoms these are 2 atoms. The first one has only first shell. Its electrons are present only in the first shell. So the distance between the electron and the nucleus is not as big as the distance in between the electron and the nucleus in case of this atom, because the outermost electrons in this atom are in the second shell. So the effect of nuclear charge, although it will have a greater proton number, but still the electrons are farther away from the nucleus. So the effect of the nuclear charge will be smaller in this atom as compared to this one. Why is that? Because the electrons in this atom are closer to the nucleus. So we can call it the effective nuclear charge. Although the nuclear charge is greater in this atom, but the effective nuclear charge is greater in this atom because of a smaller radius. These electrons will experience a stronger force of attraction from the nucleus as compared to this one, due to being closer. So this is the major factor. This is in fact the most important factor that affects ionization energy. If we compare these 2 atoms, this atom will have a higher value of ionization energy as compared to this one. This is because of the difference in atomic radius. Now moving on to the nuclear charge. Now nuclear charge is obviously a very important factor, because the number of protons, more the number of protons, they will attract the electrons more strongly, and more energy will be required to remove those electrons. But this factor of nuclear charge is effective only when we are talking about the electrons of the same shell. See, if we are talking about, we are comparing two different atoms. The outermost shell of both the atoms is the second shell. But there is a different number of protons in their nucleus. The proton number of this compound is 6 and the proton number of this compound is 5. So the radius is approximately the same, although it is not exactly the same, but still it is approximately the same because of the same outermost shell. But there is a stronger nuclear attraction in this case when there are 6 protons. So due to that stronger attraction, there will be a greater amount of energy required to remove an electron from the outermost shell of this atom. While this atom has one less proton, so there will be a weaker force of attraction relatively. So a smaller amount of energy will be required to remove the electron from the outermost shell of this atom. Now let us move on to the shielding effect. Now first of all, we need to understand that what is shielding effect. Now suppose we want to remove this electron from the outermost shell of this atom. There is a force which we have to overcome. That force is the nuclear attraction. But there is another force. There is an electron pair between nucleus and the outermost electrons. These electrons are obviously negatively charged and the outermost electrons are also negatively charged. So there is a repulsion between these electrons, these inner electrons and the valence electrons. So this repulsion pushes this electron outwards. It is favoring the atom to, favoring the electron to be removed from the atom. So this is working against the nuclear effect. It is working as a shield against the nuclear attraction. So this effect, this repulsion due to the inner electrons is called shielding effect. So we can obviously predict that the ionization energy is going to be inversely proportional to the shielding effect. Greater the shielding effect, it would be easier for us to remove an electron from the outermost shell. So let's first define the shielding effect. Now let's move on to the minor factors. First, we have the repulsion due to the electron pairs in valence shell. Now this is actually sort of a shielding effect, but not exactly the shielding effect. See, suppose we are talking about this electron. This electron will be pushed away from the nucleus due to these inner electrons, but this electron pair, this extra electron pair is also pushing it outwards, but not exactly in the same direction as the inner electrons. It is pushing it in an angular way because there is a repulsion between this electron pair and this electron to be removed too. So that force of repulsion is not as strong as this shielding effect, but still this is a force. This is a minor force which will lower the amount of ionization energy. So the greater the number of electron pairs present in the valence shell, excluding the one that we are about to remove from the outermost shell. Other than that electron or electron pair, the number of pairs present in the outermost shell, they push the electrons outwards, so they decrease the ionization energy. So the number of electron pairs would be inversely proportional to the ionization energy. Okay, now moving on to the stability of a subshell. Keep in mind we are talking about a subshell, not a shell. We are talking about subshell, like we are talking about either S subshell or the P subshell or D subshell. See, the stability of a subshell, what does it mean? a subshell is stable in two forms. It is completely stable when it is completely filled, and it is partially stable when it is half filled. For example, we know that p subshell can hold a maximum of 6 electrons. So if the p subshell is completely filled, that means it contains 6 electrons, full 6 electrons, then it is completely stable. And if we want to remove an electron from a completely stable subshell, we would need to give some extra amount of energy to those electrons. So it will increase the amount of ionization energy. The other form in which it is stable is if the p subshell contains 3 electrons, because that way it is half filled, and when a subshell is half filled, it is partially stable, not completely stable but partially stable. So in order to remove an electron from a partially stable subshell, again we will have to give it some extra amount of energy. So all other forms of this p subshell, like if there were p1 or p2, or the p subshell contained 4 electrons or 5 electrons, they are all, in all those cases, the p subshell is unstable. In this case it is completely stable, in this case it is partially stable. In all of these cases p subshell is not stable. So it would be easier to remove an electron from an unstable subshell than a partially stable or a completely stable subshell. You can note this down this way. Completely filled and half filled subshells are more stable, so the electrons need a higher energy to be removed from these subshells. Okay, the last one is if the electron to be removed is paired or unpaired. See, the unpaired electrons are relatively easier to remove. They require a smaller amount of energy as compared to an electron which is a part of a pair. What are paired electrons? The electrons which are present in the same orbital. For example, if we are talking about the electronic configuration of an element, that is, suppose it ends in p subshell and it has five electrons in p subshell, and we are comparing it to another atom whose outermost subshell is again p, but it has 6 electrons in its outermost subshell, the p subshell. So the first thing that clicks to the mind is that this subshell is completely filled, so there will be an extra amount of energy required to remove the electron from this subshell. But there is another thing. This electron, the electron to be removed from this subshell, is part of a pair, because all the electrons are paired. There is no unpaired electron. So if we want to remove this electron from a pair, it will need a higher amount of energy to be removed. But in the case of the first one, this atom, it has an unpaired electron. So if we start giving it energy, it will require a little smaller amount of energy as compared to this one to be removed from the outermost shell, because this is unpaired. The reason behind this is actually related to the stability of an orbital. Just like a shell is stable when it is completely filled and a subshell is stable when it is completely filled, similarly an orbital too is stable when it is completely filled. But this stability is not that much of a stability as compared to the stability of a subshell. This is why this factor is here at the last. So you just simply need to remember that unpaired electrons are a little easier to remove than paired electrons. Okay, so these are the factors that affect ionization energy, major factors and the minor factors. Okay, now basically most of the explanations of trends of ionization energies are explainable through the major factors only. But in the trends of ionization energies, there are some exceptions. Whenever you see those exceptions, look for the reasons in minor factors, because major factors are still the same. But if there are more than one minor factors opposing that major factor, then there is a fair possibility that it may overcome the major factor and the trend is different in that particular situation. So for the exceptions, you will find the answers in these. I will explain the trends. I will tell you the trends and then explain the reasons why the trends are that way. I hope that would be helpful for you. First, the trend of ionization energies down the group. Ionization energies decrease down the group. When we move in a group from top to bottom in the periodic table, the ionization energies of elements decrease. Like if we are talking about group 1 elements, there is lithium at the top. It would have the highest ionization energy. Below lithium there is sodium, which will have a slightly lower ionization energy. Potassium will have an even lower ionization energy, and so on. So the ionization energy always decreases down the group. And if you are asked about that, there are two simple reasons to that. See, first reason is obviously the increase in atomic radius. That is the most major factor. Ionization energy would decrease because as we go down the group, one shell is increasing. As we move on from element to element, one shell is increasing in each element. That means the radius is significantly increasing, and when the radius is significantly increasing, that means the effective nuclear charge is significantly decreasing. So due to the decrease in effective nuclear charge, the amount of energy required to remove an electron will be smaller. So the ionization energies decrease down the group. You must note down the reasons, the explanations that I told you. If you are comparing two elements which are above or below each other in the same group of the periodic table, the element which is lower in that group will always have a lower ionization energy because of two simple reasons. One, because of greater radius there is a smaller nuclear charge, and the second reason is the increase in shielding effect. Greater the shielding effect, smaller will be the ionization energy. So these are the two reasons. One. Now let us take a look at the trend of ionization energies across a period when we move from left to right in a period. Okay, when we move left to right in a period, the ionization energy increases. The general trend of ionization energies across a period is an increase, the trend of increase. But that trend is not as regular as the trend down the group. There are some exceptions in that. So first we need to look at the reasons behind the general trend. The general trend is an increase. The first reason is obviously the increase in nuclear charge, because as we move along in the period from left to right, from element to element, the number of protons is increasing, but the outermost shell is the same. Like if we are talking about period number 2, we are moving from left to right in period number 2. The outermost shell in all those elements is the second shell. But the number of protons is increasing as we move from left to right. That will cause a stronger effective nuclear charge. When a stronger effective nuclear charge is present, it would require more energy. It would require us to give more energy to the electron to be removed. So this is the reason number one behind the increase in ionization energies across the period. And the second reason is the atomic radius. Atomic radius actually decreases across a period. Although the shell is the same, like if we are talking about period number 2, all of those elements in period number 2 have second shell as their outermost shell. But due to an increase in protons, there is a stronger force of attraction to the valence electrons. And due to that stronger force of attraction, the electrons in the outermost shell are arranged a little closer to the nucleus. So the radius is decreasing across a period just a little bit, not as much as when a shell is being changed, but still there is a little decrease in the atomic radius. And when there is a decrease in atomic radius, there is a greater amount of energy required to remove the electron. So these are the two major reasons which explain the general trend of ionization energy across the period. So now let us take a look at the trend of ionization energies across third period. As you can see, I have drawn a graphical representation of that trend, starting from sodium ending with argon. These are all the elements in the third period of the periodic table, and generally there is an increase in ionization energies with two exceptions. See, in case of when we move from magnesium to aluminium, in this case ionization energy is decreasing instead of being increased. Similarly, when we move from phosphorus to sulfur, ionization energy of sulfur is less than phosphorus, it's not increasing. So these are the two exceptions in this. All other are following the trend. The general trend was increase, and all other elements are following the trend. Like when we move from sodium to magnesium, there is an increase in ionization energy. From aluminium to silicon, then silicon to phosphorus, increase. Sulfur to chlorine, chlorine to argon, increase. Now this is the general trend. These are all the elements which are following the general trend, and in order to explain the general trend, we can use the major factors, and there are two major factors which will explain all of these increases. One is the increase in nuclear charge, and the other one is the decrease in the atomic radius. But these two exceptions, aluminium and sulfur, these two are the exceptions. They are decreasing. In these cases, ionization energies are decreasing. So these cannot be explained by the major factors. There must be minor factors involved in these. Now let us compare the electronic configurations of magnesium and aluminium. See, the proton number of magnesium is 12, and its electronic configuration is like this: 1s2, 2s2, 2p6 and 3s2. And that of aluminium is 1s2, 2s2, 2p6 and 3s2 and 3p1. Okay, now aluminium is after magnesium in the third period of the periodic table, but its ionization energy is not greater than that of magnesium. It is smaller. Why is that? Let us compare these electronic configurations, and we have to look into the minor factors. See, the first minor factor is the presence of an extra electron pair in the outermost shell. Is that applicable for this or not? Let us take a look. See, when we want to remove an electron from the outermost shell of magnesium, that electron is itself part of this pair. So there is no other pair to repel this electron. There is no other pair in that outermost shell to repel this electron. There is only one pair in the outermost shell, and the electron to be removed is a part of that pair. But in case of aluminium, this electron will be removed first, and 3s and 3p, they combine to make the third shell, the outermost shell of the atom. So there is an extra electron pair which will repel this electron. Due to that, there will be a slight decrease in ionization energy. So that is the first factor which explains this trend of decrease in aluminium's ionization energy as compared to magnesium's. Now let us take a look at the other minor factors. What about the stability of a subshell? See, the electron to be removed from magnesium is a part of the S subshell, 3s subshell, and it has 2 electrons, and an S subshell can hold only 2 electrons. That means it is completely filled. So this completely filled subshell is stable, so it would require an extra amount of energy to be removed. But in this case, the electron to be removed is present in P, the P subshell, and the P subshell is neither completely filled nor half filled. That means it is unstable. So the amount of energy required to remove this electron will be smaller as compared to the amount of energy required to remove an electron from a stable S subshell. So these two minor factors are favoring this exception. They are the reasons of this exception. Let us take a look at the last exception, the last minor factor actually. The last minor factor was if the electron to be removed is paired or unpaired. And I told you unpaired electrons are easier to remove, and we already know if we want to remove an electron from magnesium's outermost shell, that is part of a pair. So it would require a little more energy. In case of aluminium, the electron to be removed is unpaired, so it will require a little smaller energy as compared to that. So three minor factors are combinedly working against the two major factors. This is why aluminium's ionization energy is a little less than that of magnesium. Now let us compare the ionization energies of phosphorus and sulfur. Again, sulfur is after phosphorus when we move from left to right in the third period of the periodic table, but ionization energy of sulfur is a little less than that of phosphorus. To explain that, we'll take a look at the electronic configurations of these two elements. The proton number of phosphorus is 15 and sulfur is 16. So the electronic configuration of phosphorus would be like this. And that of sulfur will be like this. Okay, now let us compare these two electronic configurations. Now first thing, the first major factor was the repulsion due to an extra electron pair in the valence shell. Now let us see if there is an extra electron pair or not. Well, yes, there is. This electron pair. Suppose the electron to be removed from the outermost shell of phosphorus is this one. We need to remove this electron, and from sulfur, this electron needs to be removed. Now this is the outermost shell of phosphorus atom, and this is the outermost shell of sulfur atom. In case of phosphorus atom, there is only one electron pair in the outermost shell which will be repelling those electrons. But in case of sulfur, there are two electron pairs, one in 3s and the other one in 3px. So there is an extra repulsion on this electron as compared to that one. This is why it would require a little smaller amount of energy to be removed from the outermost shell. Now let us take a look at the second minor factor. What was that? It was stability of a subshell. If you look at the electronic configuration of phosphorus, you can see that its p subshell, 3p subshell, is half filled. It contains 3 electrons, and as I told you, half filled subshells are partially stable, and a little more amount of energy is required to remove an electron from a stable subshell. But when we see the outermost subshell of sulfur atom, it is neither completely filled nor half filled. It has 4 electrons, so it is unstable. So the amount of energy required to remove an electron from this subshell would be a little smaller as compared to that one of phosphorus. So these are the 2 minor factors which combine together to work against the major factors, and the ionization energy of sulfur is a little less than that of phosphorus. Keep in mind that both the electrons to be removed are unpaired, so the last minor factor, the paired or unpaired electron, that factor is not applicable to this explanation. So there will be only 2 reasons behind this exception. Rest of all the exceptions will be explained by the major factors. One, increase in nuclear charge, and the second one, decrease in atomic radius. I would suggest you all to write the explanations of each change in ionization energy in your notebooks and prepare them. I mean, you have watched the video. If you have understood the concepts, do not just note it down by watching the video alongside. Just try to understand the main concept behind this. Note the factors down in your notebooks. After that, draw the trend in your notebook and write each explanation, the explanations for each change in ionization energy by yourself. That would help you to understand the concept too, and that would help you to answer the examination questions. I hope this video was helpful. Do practice the questions from past papers about this topic, and let me know if you still have any problems or confusions about this topic. I will try to explain those problems in my next video. Thank you very much. Allah Hafiz.